why should we care? What impact is this going to make on the world?
Well, I have to go, what? You don't care how the brain works?
Right. What is wrong with you?
How can you not care?
Right. Welcome to HolyShift, Biomedical Breakthrough Shaping Tomorrow. What is biomedical engineering exactly? It's about engineering solutions that improve human health, from new medical imaging tools to personalized cancer treatments. HolyShift reveals the people, passion, and purpose powering the future of biomedical research. Our guest today is Professor Shella Keilholz from the Biomedical Engineering Department at Georgia Tech and Emory University. Dr. Keilholz uses some of the world's most powerful MRI scans to explore what's really happening inside the brain. Outside the lab, she's a master of martial arts. But don't worry, this conversation stays strictly non-physical. So join us for a dive into how understanding brain signals can change the future of neuroscience and medicine. Well, welcome to the HolyShift podcast, Biomedical Breakthrough Shaping Tomorrow. We are kicking off the new year. This will be released much later than New Year, but we are kicking off the new year in January with you to tell us your story. So why don't you introduce yourself and tell us why you're here?
So I'm Shella Keilholz. I'm a professor in the Wallace H. Coulter Department of Biomedical Engineering at Emory University and Georgia Tech. It's a long mouthful, but I think I managed to get it all in.
Amazing. Yeah. Well, why don't we kick off and you tell us, when you talk about the work that you do, how do you describe it to most people in the world?
So if it's one of those, brief encounters and somebody says, well, what do you do? And you try to kind of condense it down. I either say imaging or I do brains. We're kind of at the confluence of both in reality, but, it's complicated to get into that with kind of a short conversation. But what is exciting to me is that both of these fields are full of complex and interesting questions. And when you put them together, they kind of enhance each other in synergistic ways.
So when you think about brain and imaging, then, when I think of imaging for the brain, I think of MRI scanners. Maybe some of our audience might have heard of them, where they know someone who's had to have one after they've had like a head trauma or something like that, or they may have a brain cancer and they may need to go in and do some imaging like that. How do you use imaging, and are you doing research on the brain and research on imaging, or researching on imaging of the brain, and what does success look like in that research?
Thank you for making my research area a little bit cleaner. And you mentioned MRI, which just happens to be my very favorite imaging technique. Imaging encompasses a lot of things. Started with X-rays about 100 years ago. This first chance that we got to look inside the body without hurting anyone or having to do an incision. It's amazing if you think about it. And then we've got MRI, and MRI lets you look at not just bones, but like different kinds of tissue. So it's exactly what you would need if you had had some kind of head injury and you wanted to see if your brain was okay. And that same contrast makes it really exciting to use to study the brain. One of the cool things about MRI is that you can look at structural features like, how things are wired, kind of where the main pathways in the brain are. You can kind of think of it as like a map, like a city map with all the different roads and pathways. And you can see where the traffic might go. So that's one thing you can get with the MRI. The other thing you can get is the activity. So maybe that would be like looking at where all the people are in a city.
Oh, I love this.
So you see everybody flow in for work, and they're all downtown, and then at night there's this exodus along the major roads, and people spread out to do other things. And we're looking at these same kind of patterns in the brain with the imaging technology that allows us to do it.
Okay, so what I was just picturing when you were talking about that, I was thinking about the evolution of maps, like the day before they had maps, and then they had the paper maps that we grew up with, and then they have the Google Maps, and now Google Maps will tell you all the traffic, where the police are, where the objects on the road are, all of that type of additional. So that's kind of the trajectory of what MRIs has done, from seeing nothing to X-rays to MRIs. Now, what is it about the brain that you and your team are most interested in then?
So, it took me a while to understand how interesting the brain is.
Tell me more.
I think as a graduate student, I was focused on imaging other things.
Okay.
And we were trying to look at things like the kidneys and the liver And you probably don't realize this, but your internal organs are moving around all the time as you breathe and as your heart beats. And so to get good images, you had to try to correct for that motion.
Yeah.
So I thought that was fascinating.
Yeah.
And I thought, oh, the brain is so boring. It doesn't move. It just sits there. So I wanted to do anything but the brain.
Oh, I love this.
But then I had a chance to go to the NIH, National Institutes of Health, and work with somebody who had one of the only high-field scanners in the world at that point.
So what's the difference between a high-field scanner and a scanner that you might find at your local hospital?
So the scanners you find at the local hospital all involve large magnets. So if you've seen an MRI or if you've had an MRI, you have to go down that tube. That tube is basically a giant magnet.
Okay.
And so the bigger the magnet, the more signal we can get and the better image that we can make. So he had one that instead of maybe 1.5 Tesla, which is just a magnetic field measurement that you have at the hospital, was 11.7 Tesla. So
oh my gosh.
Almost 10 times as strong.
I seriously have only heard of 1.5 Tesla and 3 Tesla. I had no idea there was such a thing as that big.
They're starting to make them for humans, just for research purposes right now. But even here at Emory, there is a 7 Tesla MRI scanner now. We just got it within the last year or two.
Okay.
And it is getting beautiful images of the brain, just fantastic.
Wow. Oh, I can already envision. You know what it makes me now think about, like the generation of movies, right?
Yes.
And graphics and how now you can see. And I think maybe that granularity or how much better you can see those images than if you're looking for the smaller and smaller changes that could have a big impact. You would be able to see it in there.
That is exactly right.
Okay.
And one of the things that my lab is really interested is understanding how brain function changes over time. So to go back to your analogy, for a long time it was like we would take these long scans, 10, 20 minutes, and make one map.
Okay.
One map that said, oh, this area is more active, when you're doing math or whatever. Now we're starting to look at how things change over time. And that is important and super exciting to me because one of the things that we really don't understand well about the brain at all is this variability.
Okay.
So, why don't I respond the same way all the time, even if I'm trying to do something very simple, right? If I'm reaching out to press a button even, I move a little bit differently every time. From sports, if you've ever done a sport or a physical activity, maybe you're trying to perfect your golf swing. We can't do it quite the same.
Right, because time. You get it right one time and your coach says, yes, exactly like that. And then you cannot replicate it to save your life.
And you can't do it.
Yes.
Exactly. So there's this variability.
Okay.
And we believe that the source of that variability is in your brain. Oh. And more specifically, we believe that it's related to kind of these weather patterns of brain activity. So that you have to look at the whole brain, and you have to look at how it's changing to be able to understand how activity related to this one particular thing that you're trying to do is affected by all of this other stuff. So we're very excited about getting these high-field MRIs because that's enabling this new approach to brain imaging and letting us see things that we could never see before.
Now, when you mentioned earlier about it and you said looking at changes over time, what is that amount of time you're looking at?
So right now, in our studies in humans, we're looking at about a second.
Okay.
So we can see second-to-second fluctuations.
Wow.
Which I think is really super cool to be able to image the entire brain in less than a second with, such good image quality that you can easily see borders between different areas and things like blood vessels and these pathways in the brain. So really, really amazing stuff.
Okay, so to be devil's advocate then for a moment, so what? Why should we care? What impact is this going to make on the world?
Yeah, well, I have to go, what? You don't care how the brain works?
Right. What is wrong
really?
with you?
How can you not care?
Right.
But I think to be a little bit more concrete,
right.
I think there are a lot of things that could help. And, of course, clinical applications of any type. And one of the ones that I like to point to is there are a lot of people who are trying to use some kind of neuromodulation now. People will put in electrodes and try to stimulate certain areas of the brain to treat chronic depression.
Okay.
They've been doing this for things like Parkinson's for years.
Yes.
But now there are these more non-invasive approaches where you can do the same kind of stimulation from outside. But if we really want to have an effect, we need to know not just where, but when to do that stimulation for each individual. We need to be able to understand, how things are evolving. What does the weather look like? And how do we steer the weather to where we want it to be? So that's something I'm super excited about.
Yeah, I love that because one of the things I'm now hearing you say this that I didn't realize before we started talking today is that how important it is to be able to understand that variability and anything that could potentially impact that, so that when we're trying to get these advanced technologies to be able to help the patients that have them, you also understand how to maybe recognize when they react a little bit different and how you might be able to adjust the stimulation to accommodate for that.
Exactly. I mean, this is a major goal of biomedical engineering in general, right? Is to move from medicine that's based on average or typical patients to medicine that is tailor-made for you.
Yes, which is amazing. Okay, how did you get interested in just this field in general? What made you decide at some point, hey, I want to study 11 Tesla MRIs, the impact on the brain? What was curious about it for you?
Well, I was a physicist when I was in college, and I kind of arrived at that by random, looking at science. I liked all the science, but I thought, well, biology is kind of applied chemistry. Chemistry is kind of applied physics. Maybe I'll start at the bottom and work my way up.
Okay.
Well, I never got past physics, of course, but so I like the physics, and MRI has a lot of interesting physics.
Yes.
But the other piece that I wanted was some way to help people. I looked into medical school. I looked into, medical research, and I wanted something that could kind of combine what we do in physics with some kind of application that would have, more immediate and obvious outcomes on human health.
Okay, so is this what you wanted to do when you were 5 years old?
No.
What did you want to do when you were 5?
I think I wanted to be a truck driver.
Oh, I love it. Did you see someone that was a truck driver and think that is a really cool job?
I did. I knew one of my friends was, his dad was a truck driver, and he had this giant truck.
Okay.
And he went all over in this giant truck, and I thought it was amazing. So...
Well, now, I mean, there's so much more research you can do in that area, but that is awesome. So you obviously pivoted from truck driving as your life goal and went into neuroscience. What did that journey look like for you?
I was a curious kid. I think most kids are. Mm-hmm. And my dad really encouraged it. And he's always had a lot of interest in nature and curiosity about nature. So he was always, helping me figure out, where do you find mushrooms? You have to look for this kind of tree to find this kind of mushrooms, telling me about plants, about stars, about weather, all of these things that we could see out in nature. And I think that just kind of sucked me into science. And then they had some science programs for kids, and I got to attend a few of those, and I loved it. So when I realized that was something that you could do for the rest of your life, and people would not just let you have access to a lab to do it in, but actually then pay you to do it, that was amazing.
Oh, yeah, that's exciting. So let's talk a little bit then when you talk about paying and the cost of science. I think a lot of the world, it's hard to understand, which is why I was devil's advocate a moment ago. Like, what do we need to learn about the brain and in these instances? There's so much that we can gather that can have a huge impact on society. But that also is really, really expensive. So how do you navigate doing the research, having a team, and I also want to learn more about the team that works with you, but how do you navigate that and find the funding and the partner so that you can drive success?
Well, first of all, I should say thank you, because your tax money and my tax money is what funds a lot of our research. And I think knowing that gives us a perspective. My lab is constantly asking, are we working on the most important question we can address? What is the thing that we can do right now that is most important to, our goal of understanding the brain? Because we don't want to waste our money.
Right.
Or your money.
Yeah, I love this, yeah.
And we rely on the federal government for funding because the work that I do is more basic science. So when I think about research, sometimes I think of it as a journey, right? And there are different types of journeys you can take. Sometimes you can see where you want to go. And, it's like looking at the top of a mountain. It's there. You can get there. You just don't know how yet. And I think that kind of research maybe has a little bit more chance of getting funded by some of the drug companies, especially if you can see the peak from not too far away, right?
Yes,
it doesn't take too much to get there. or some of the other medical companies. But the kind of research that my lab works on is more like this exploratory research where we suddenly stumbled upon a whole new continent. And now we have to see what's there and what might be useful about it. And it's not the kind of thing that has an immediate application, where you can take it next week and commercialize it and make money off of it. But it is the kind of thing that has really broad effects. So we may not just get to the top of the mountain. We might be able to collect a bunch of new plants, find some new animals, find a new place to farm. Who knows? All of these things that we could discover on our new continent, right? And so I think that because we're at the fundamental level, we don't have as much potential for direct investment, but we have potentially greater impact overall.
How do you describe that to potential donors or potential grants that you might apply for? Because I think one of the things about basic science that is missed is how that basic science, as you just talked about, it ends up being the core that you need to do any other science at any point, right? I was just on a call yesterday, and it was dealing with a drug that someone at Emory had invented, and it was for this one focused area. And then suddenly you realized it is totally applicable in something completely different. And when I think about those basic science has that ability when you start understanding these things to then the next person come in and say, wait, this piece that she figured out now can have this major impact. How do you describe and get funding and get people to buy into that idea?
So, we try to talk about specific projects. And I'm sure that we're not envisioning all of the right applications for the things we're going to find, especially because we don't know exactly what we're going to find.
Right.
But we have some ideas. And so I mentioned the thing about targeted neuromodulation for certain disorders. That's one direction that we like to talk about. Another that is completely outside of the medical field is for AI. If we understand how the human brain works, we can do a much better job of designing these algorithms that replicate it and do work that we want our computer programs to work with. You can argue whether that's a good thing or a bad thing, but I think understanding it is critical.
Yes, yeah. Well, absolutely. Understanding it can then help also. The more we understand it, the more we can drive it towards good.
Exactly.
As well.
Exactly.
Yeah. Okay. So tell us a little bit more about the team that works with you. Who are some of your teammates that work with you? Have any of them maybe journeyed off into other directions and are doing research in some other areas that you can share with us?
One of the things I love about science is that we have such an interdisciplinary network. And so in my lab, we bring people in from electrical engineering, computer science, biomedical engineering, biology, the neuroscience program. I've had MD, PhD students come in. So we have this really wide range of expertise. And then we collaborate with faculty who are working in all of those areas too. So it's this very cool situation whenever we have lab meetings. I get to learn from all of these people. And I think people don't realize that goes on so much, that you learn as much from your students as, I hope my students are learning from me as well. But we learn from each other. And that's why the wide range of, backgrounds and expertises is so important, because it lets us have a broader perspective that makes it more likely we're going to find that new continent.
Yes, because people that come from different backgrounds, they hear things and they react to things slightly different.
Absolutely.
So we might say something and then they may connect dots that we would never connect.
Exactly.
Which is amazing. That's so powerful.
Exactly.
How do you foster that so as a team leader, for example, how do you encourage people to speak up and maybe even give ideas that might be different from what you anticipate?
I think a lot of it is attitude, but I don't think it's very hard, really, because I feel like a lot of the people who, are kind of drawn to this area are curious and they want to know. And really it's this quest for knowledge that's driving all of our interactions, right? And if that's true, you welcome anybody who is willing to, give you an idea or help you to get a little bit further along in that pathway. So I think, we've managed to always have this appreciation that everybody brings value of different kinds.
What would you think So if you could imagine someone who's not into science at all, can you think of something that would truly surprise them about the work that you do, whether it's something that's hard about it or something that's more fun than you would anticipate?
Well, I want to go back to your very first statement about that. Somebody who's not into science at all.
Yes.
Because I feel like this is a little bit of a misconception. I think people think that science is something that happens, in a few specialized labs and it's very complicated. And I don't think that's right. Science is something we all do every day. So one of my kids is a baker. She's making souffles. She's like, I want my souffle to be puffier. Well, maybe I'm going to bake it at a lower temperature for longer. That's an experiment.
Yes.
She's asking a question and doing some kind of intervention and seeing an outcome. And that's what science is. So, sure, as scientists, we've been through training, but our training is to help us find more powerful, impactful questions and to give us more rigorous and, explicatory tools to address those questions with. It's not about the process. I think that process is really kind of inherent to people. We all want to experiment.
Yep, solve problems. So what would you say then in the work that you do is the most frustrating part of your job?
The most frustrating part. Well, there are definitely times when you have tried something and tried something and tried something and it just doesn't want to work. And, I think that it's easy to get down then. And this is when...
That was what I was about to ask. How do you stay motivated when that happens?
Well, this happens for every student, yes. I think. There's always a point when you're going through a project when you're just like, this is not going to work. And you hit some kind of roadblock. You've either got to find a new direction that will take you around that roadblock or say, you know what? This is just a bad way to go. Mm-hmm. I need to turn and go over here instead. And I think learning when to do what is probably the hardest part of science. But one of the things that I always tell my students, and that I try to remember myself when I get frustrated, is that a lot of our most exciting discoveries have come through things that we were wrong about.
Can you think of a couple of examples?
Yeah. So I mentioned those movies of brain activity, right?
Yes.
Well, it turns out that if you look into the technology behind MRI, you can get these kind of weird changes from things like breathing and the heart beating.
Right.
And so when people first started reporting changes in brain activity, I said, it's just nothing. It's breathing. We're looking at people, at people breathing in the scanner. I'm like, that's nonsense. But I thought, but if it weren't, that would be so exciting. And so, we tried to do some experiments. We showed, no, actually, it's not breathing. And then we're like, okay, this is exciting. So we were wrong to begin with. But by proving that, that was wrong and that we really had something there to work with, it opened a whole new door for us.
Which is why it's important to continue this type of science. Because if we just took the knowledge we had today and just said it's good enough, the cures and the advances we could potentially do in the next 10 to 15 years would not be possible.
Absolutely. And, I think another misconception about science is that, we're settling questions. And we're not. We answer questions to the best of our knowledge at a given time. And so science does change as the years go by. If you want to take the long scale, you can look at what we thought about, the solar system, right? For years, people thought the Earth was at the center and everything went around us. And then we figured out, oh, wait, no, actually we go around the sun and things go around that. And now we're like, actually exploring the moon and trying to get to Mars. So we've come so far from what we originally knew. But it wasn't that, the science was bad. They said, oh, I see how these planets move and everything. They just didn't have the tools to investigate to the next level. And so as we develop new tools and new techniques, we're able to give better and better answers to the questions that we have.
So I'm dying. I want to see the new scanner. Is it maybe Dr. Oshinsky that works? Yes. Okay. Because I remember him telling me about a year ago this was coming, and I completely forgot about it. Okay, on my list, everyone who's in Atlanta, also you should see if there was a way you can figure out and find and learn more about that. Maybe we'll get him on here one day. Okay, so what would you say then is your favorite part of the day?
Two pieces.
Okay.
I love doing anything with my students. I love looking at their data. I love running experiments with them. I just think that is super fun. And the other thing I like is analyzing data myself. taking something that we've gotten from
Which
an
some people
experiment.
may hate. So.
I know, but getting something that we've just gotten with one of our new techniques and doing kind of the first peek inside to see what's in there is super fun.
Oh, that's amazing. Can you think of a meaningful, memorable experience that you had recently that is inspiring?
So I think it's really more the everyday events that motivate me to keep up the work. And as an example of one that recurs for every student that I have, there's a point where, you've been working with somebody on designing their experiment and, how to interpret their data. And then one day they come in and they have an idea. And they say, this is what I want to do and this is why, and I'm so excited about this. And it's like the project has become theirs.
Yes.
And they've turned into their own, independent scientist. And I love that moment. I just think that's wonderful.
Yeah. I like the glisten in their eyes.
Yes.
Because I think it's where they find this is the next piece of meaning in their life that's really exciting. And
yes.
you get to be a part of that.
Exactly. And it kind of takes me back to when, I was first finding my own, research projects and doing my own thing. And it's such an exciting time.
So tell us a little bit about who you are as a human. What do you do outside of the lab?
Oh, I have a lot of things I like to do, but probably my favorite is Aikido, which people may think is strange. It's a Japanese martial art for self-defense.
How did you get into this?
Kind of randomly. I thought everybody ought to know some self-defense.
Yep.
So when I was a grad student, I was going down the list of courses, and I said, well, karate, you have to punch people. Taekwondo, you have to kick people. I'm like, I'm not good at any of that. I said, well, here's this Aikido thing. Well, let me try it out. So I just kind of got sucked in, and it's really a lot of fun. It's a great crowd of people to practice with, so I really enjoy my time there in the dojo.
I have heard of some other people that have done it that have also found it very meditative.
I think that's
and
true.
Healing.
Yeah, so there's an aspect to probably any martial arts where you're trying to focus and pay attention to exactly what you're doing right then. And I have trouble concentrating. I'm kind of a scattered person in general. But when somebody is trying to hit me, I pay attention to what's going on. So it really helps you to be like right there in the moment.
So thinking about being in the moment and the team members that you work with, can you tell us, like, some of them may continue to do science, such as yours, and some may move on in other directions and pursue other careers. What are some other careers that you would utilize this knowledge and education for?
So I've had students who have done a wide variety of things. Some have gone on to become teachers. One was involved with a startup. Most of them are related to science in some way, just not necessarily what we do in my lab. So, for example, the person who was involved with a startup, it was in using AI to help cure neurological disorders.
Okay.
There are people who've gone to work for medical equipment companies who build the scanners. Lots of people who are doing data analysis of some kind, data science, that's become a really big field lately. So really very broad applications.
Yeah, that's exciting. So what do you really want in today? So 2026, what do you want the world to understand? If they take nothing else from the work that you're doing, what would you like them to remember and understand about it?
That we're trying to understand brain activity for personalized approaches to medicine.
I love that. So tell us what this year looks like for you in your lab. What do you think of as their major challenges, and what are you most excited about for the year to come?
Well, we have some new equipment, and that's one of the things I'm so excited about. I mentioned the 7 Tesla for humans.
Yes.
We want to play with that. There's also a new 11.7 Tesla for mice and rats at Emory now.
Ah.
So the one where there was only one in the world when I started, now there are a handful, and we've got one. So I'm excited about that.
Yeah, it is exciting to be here and have those resources.
Yeah.
What are you most anxious about for the year?
Oh, gosh. Maybe workload.
Yes, yeah.
I think one of the problems we run into is there's so much exciting so many exciting directions to pursue that it's hard to choose, and I feel like we've gotten a little bit overcommitted. We're trying to go in a lot of different directions at once. At the same time, that makes it exciting too. So it's the flip side of the coin, right? I'm worried about whether we're going to manage this, but excited to see where it goes.
Well, I think it's going to be very amazing. One of the things when I think of that workload piece too is pretty soon something's really going to move to the top, and I can't wait to hear what that discovery is or what that advance is and the impact it's going to make on the world, which is very exciting and why we want to have these conversations. So I know that part of workload, we took you away from your lab. Thank you for coming in today and sharing so much of the work that you do. I'm excited, and I know that when you do have some advances, please share them with the podcast, and listeners, we will share them with you as well. How can listeners learn more about the lab and follow the work that you're doing?
Well, we do have a lab website.
Okay.
I've got to say, we're not terribly good on social media. I'm afraid that's part of that workload problem. But yes, look at our website, contact us, and if there's anything that you're interested in seeing about, imaging at Emory, the Center for Systems Imaging Corps often has clinical trials or needs for volunteers. So you can check out maybe getting an MRI of your own brain.
Oh, that would be exciting. All right, listeners, we will put all of that information in the show notes. You can also comment on this episode, and if there are things you want to learn about the brain, comment. We will ask some experts such as this and get back to you. So thank you for tuning in to this episode of HolyShift, Biomedical Breakthroughs Shaping Tomorrow. That's it for this episode of HolyShift, Biomedical Breakthroughs Shaping Tomorrow. If today's conversation sparked your curiosity, pass it along to someone eager to explore the power of research to change lives. As a reminder, the opinions expressed in this podcast are those of the host and guest and do not represent those of any organization mentioned. Be sure to follow or subscribe wherever you get your podcasts so you never miss an episode. To learn more about the research featured on this show, visit bme.gatech.edu or check the show notes for links and resources. Thanks for listening, and remember, behind every innovation is a purpose, a person, and a powerful story.